Hello everyone, this is my another lecture on weld-induced thermal history. Here also I will discuss about the basics of heat flow in welding. So, in this lecture the topics which I will cover are as below, like that you can see in this slide. Here I will discuss first about the stages of welding process, that during welding process what are the different stages generally it is subjected to, that related thing I will discuss. After that I will discuss about the fixed heat source in welding. It is generally a line heat source or a point types of heat source. Based on this line heat source and point heat source, if it is in a fixed position, then what should be the thermal history at a particular location over a time, that you can say, that we can predict by using this fixed heat source concept. Now, after that I will go to discuss about moving point heat source. After that also I will discuss 2-dimensional and 3-dimensional heat flow, and finally if time permits I will cover this cooling rate part also. So, first of all, in previous lecture I have already derived about the governing equation of heat conduction, that is generally called Fourier heat conduction equation. So, that is also known as governing equation for thermal analysis in case of welding process. So, that is why I am writing here. So, the governing equation which we have derived last class based on Fourier heat conduction equation was del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square plus q triple dot by k is equal to rho c del t by del t. In last class I have already explained this thing very clearly. This equation generally called as Fourier transient heat conduction equation, but this equation generally here we will use for prediction of thermal history for different cases, for different types of heat source model. That is why this we will use as a governing equation for thermal analysis of welding process. That is why I have written here governing equation. So, here generally the output is, you can say, is temperature. What is temperature? And input is generally, you can say, material property. What are the material properties? So, this is your output, you can say, output, and here inputs. To get this output, what are the inputs required for this heat conduction equation, that I am going to write. So, here the input required are, what are the input? Are rho density, that is means density. In case of SI unit, its unit is generally kg per meter cube, you can write. Second one is, you can say, C, specific heat. Its specific heat, its unit is generally, you can write joule per kg Kelvin. And what are the other things? K is called thermal conductivity. Thermal conductivity, its unit is generally watt per meter Kelvin. This is very well known to you. Then also in SI unit I am writing these things. And Q triple dot generally I told you is a volumetric heat source or heat generation model, or you can say this is the Q dot triple dot is volumetric heat generation rate per unit volume. Its unit generally is watt per meter cube. So, last class already I have explained these things in details. So, today based on this governing equation and different what it is called boundary condition and initial condition, I will show you what are the different solution we can get for what is called fixed heat source model, then moving heat source model. So, if a particular plate, if there will be a point heat source, due to this point its source, if it is not moving, that means fixed. Due to this, what should be the temperature distribution at a point over time, what should be its solution. Based on this equation, generally that solution how it is coming, that things in details I will discuss in this today's lecture. So, I will show you actually different solution based on this governing equation and different boundary condition, that related thing in detail in today's lecture I will discuss. So, in this equation, generally this equation is applicable for isotopic types of material, isotopic homogeneous types of material, because here generally we consider Kx is equal to Ky is equal to Kz is equal to your K, that you can see. Now, here this equation further can be written in terms of thermal diffusivity is del 2 T by del x square plus del 2 T by del y square plus del 2 T by del z square plus Q triple dot by K is equal to 1 by alpha. This alpha is called thermal diffusivity del T by del T. So, this alpha here I am writing is called thermal diffusivity, thermal diffusivity. I have already discussed this thing, which is equal to actually you should keep it in mind K by rho C, that is why I have written 1 by alpha. So, from this equation also itself you can get the idea how this temperature is varying. That means, here you can say if a material have high thermal conductivity, you can see, then high thermal conductivity means the temperature rise, you can say peak temperature rise will be generally less, that way you can tell, because high thermal conductivity means very quickly the temperature will conduct, then your rising of temperature for a particular heat input will decrease, that you can see inversely proportional. Here you can see this left side temperature, right side your material property with a specific heat, also you can how it is varying, everything is given here, everything in details one by one I will discuss in subsequent slide. Okay. So, now I am going to discuss about what are the generally stages we can see in case of a welding process. In case of a welding process, you can see in this figure we can see 3 different stages, or you can say the following stages, that you can say this first and at last you can see 2 different tangent stages, and in between also we can get another stage, that stage is called quasi-static stage. What is this stage? That related thing little bit I am going to discuss here, because you see, let us consider this is a weld plate which I have already drawn here. So, once the welding start from here, then you can observe that during starting of the welding, immediately the temperature is not go to its peak temperature. So, here generally you can say the thermal profile is in this stage, this thermal profile is generally you can say gradually increasing. That means, here you can see the temperature is rising stage. So, here the temperature you can say this temperature profile in case of welding, generally what happens due to heating and cooling effect with time, how the temperature distribution generally you can get at a particular point, that little bit I am just showing. Like let us consider this is your temperature and this is your time axis. Okay. T is capital T is temperature, this is your I am writing time, and this is your I am writing temperature. Okay. So, in case of welding, what happens during heating, the temperature rise with time rapidly. Once this heat source move away from that location, there generally it start cooling, and it is due to coolings after a certain time what happen, it's return back to its room temperature. So, this is generally you can say this is generally heating phase, and this is generally this is heating phase, you can say here due to the thermal conductivity, and heat input generally with time temperature is rising at a particular point, and once this heating is start cooling due to convection and surrounding conduction and radiation types of phenomena, it start generally cooling, and with certain time, generally with time, this temperature start decreasing in nature. So, at a particular point at the starting, generally suddenly it is not go to its very peak temperature. Here generally what happens, gradually generally it absorbs the heat from that what it is called heat source, and in that location generally what happens, the temperature start gradually rising in nature. Okay. So, during a starting time you will find there is a temperature means rising stage where the temperature is rising in nature. So, this is a particular length, that length generally it is subjected to where here peak temperature is not constant. So, after that generally we will observe that after that your temperature profile, once it goes to a particular peak temperature, after that you will observe that temperature is not, or temperature profile at different location you can say, which is remain almost same types of profile, which is remain almost same types of that means here you can see your peak temperature, here if you draw a peak temperature which I have shown at top of this plate, peak temperature means this temperature is called peak temperature of that point. Okay. Similarly, here also peak temperature is this, peak temperature is this. So, this peak temperature generally remain in a constant level, that you can see. So, this stage where generally temperature profile does not change, that you can say, temperature profile does not change, that zone is generally called quasi stationary or quasi static zone, which I have written in this figure, you can see. So, in this zone generally what happens, this quasi static zone can be defined at which the temperature distribution is stationary. This stationary is about what? About a coordinate, that coordinate system is moving with heat source, that coordinate system is moving with heat source, I have already written. So, this quasi stationary state, here generally temperature does not change with time, that you can say, profile is not change with time, if we will observe about moving heat source, this you should keep it in mind. So, this is generally called quasi stationary state. After that generally what happens, once you extinguish the arc, at that generally you will find this peak temperature level further stays decreasing in nature, okay, gradually decreasing in nature, what I am telling, understand, that means temperature profile, because extinguishing here is temperature generally over the distance here you can see, which is gradually decreasing in nature. This is called second transient stage, this you should, and this is called, this first transient stage has a name, this is called initiation stage or initial transient stage, initiation stage, and this middle stage is called quasi stationary stage. Generally whatever the solution we will show you in this lecture, most of the solution is based on this quasi stationary zone. And another things you should keep it in mind, generally why most of the solution is based on this quasi stationary, and this is the most important zone you can say, because most of the thermal expansion, contraction, that means which is significant you can say, is generally occur in this quasi stationary zone. And most of the variation also you can say, like heat affected zone variation, then what is called well zone variation, microstructural variation, most of the thing generally, and deformation and residual stress and all the thing, most of the thing generally significantly you can observe in this quasi stationary zone. That is why this based on this quasi stationary zone, lot of what it is called different solution are available for weld related what is called thermal field, that I will going to discuss in subsequent slide. So, that is why I have here written the majority of the thermal expansion and shrinkage in base material as well as in heat effector zone occur at quasi stationary stage. This I have already written. Now, we will discuss the quasi stationary temperature distribution over a what is called well line, how it is varying. Okay. So, let us, I am drawing this thing. So, what we observed in previous slide, there are two different stages, one is called transient stage and another one is called quasi stationary stage. So, in transient state we observe that what is transient? Transient means which is time dependent, that means with time your temperature is varying, whereas in quasi stationary stage which is not time dependent. That means the quasi stationary state you can say is that the temperature will not vary with time. When it will not vary with time, when we will observe this temperature profile about a point which is following the heat source. That means, with respect to moving heat source, if we observe that thermal profile around the heat source, we will observe it is remained constant over time, that you can say. That also I have shown in previous slide. That means, the usually peak temperature, if you observe the peak temperature at the position of peak temperature point, you will observe that over this quasi stationary states this peak temperature remain constant over time, it is not varying. Similarly, in other location also if you observe about this moving heat source, you will observe that temperature also is not varying. But if you will observe that things about some stationary coordinate system, you will observe at that location with time temperature profile is varying, it will varying. Now, first of all I will show you along the what is called well line how the temperature distribution is looks like, little bit a systematic or you can say a mimicking of welding relative temperature distribution at different position about weld center line, how it is varying, that I will discuss now. So, let us consider this is the weld's center line, that means along this welding is, this is also welding direction, I am writing weld center line along this direction, rightward direction welding is taken place. Now, here generally how the thermal profile is looks like, that thermal profile in the sense overall temperature profile its look like, that I am going to show. And let us consider this is this vertical axis represent your temperature, little bit I am showing, then it will be very clear to you. So, you will observe that the temperature profile which is looks like so, what you can observe here, little bit bigger way I am just showing. So, this is weld center line, here generally x is equal to you can write as welding velocity into time, with time generally it is varying. So, this from here to here what happens, this zone is generally called weld pull zone. Let us consider at weld pull zone how the peak temperature distribution is look like, that I am showing weld pull zone. So, in weld pull zone, in case of steel generally it is varying from let us what happens your what is the temperature level, melting point temperature is around 1540 degrees centigrade, you know these things approximately this. And in case of a welding process generally arc, especially arc welding process, here the peak temperature at the weld pull center line can be around approximately 2200 degrees centigrade, generally it is varying 2000 to 2500 degree centigrade, that is why I have written approximately that temperature level. So, this is generally called molten pool zone. Let us see, this is actually your molten pool zone I have written, and here where the peak temperature is achieving, that peak temperature have a name, that is called root of arc, root of arc zone. That means where the maximum temperature or center line intensity, actually that you can say, center line intensity of your arc, whatever the arc generally we are using to do the welding. So, this is called root of arc. Now, just after that you see, due to heat conduction ahead of the welding, you will see ahead of the welding there will be, due to heat conduction there will be some temperature, you see there will be some temperature, but after certain distance ahead of the, you can say molten pool, your temperature will be room temperature. Here I have drawn, here let this is your room temperature. Similarly, at back side also you will observe, when the heat source move, this molten pool moves here, generally this heat source start moving from this location, okay. It will start moving in this location, this way it is going, okay. This way it is going, this is the molten pool heat source moving I am showing, okay. So, here you see, so in this zone let us weld material already solidify, weld material already solidify. So, this is generally called solidified weld zone, this you can write, okay. So, solidified weld zone, here generally close to the weld pool zone your temperature will be closer to melting point temperature, that is approximately 1540 degree centigrade, and after that generally due to this cooling what happens, here the temperature will gradually decrease. So, this has a name. What is the name of this? This is called mnemotechnical way of what it is called, describing such a condition, that is which is compare the temperature field around the heat source in a what is called temperature mountain moving in the direction of welding, okay. This is called mnemotechnical way of representing temperature distribution around a heat source. What I am telling, understand? That means along weld line how the temperature general distribution, but generally what happens. So, for every position, generally for this position, so every position these types of generally we will find these types of mnemotechnical temperature mountain, that you can say, which is generally moving along weld line. Now, here you can see there is a step at, here you can see there is a step. Why this step is there? Because here generally material is start solidifying. So, once material starts solidifying, there generally it is generally transfer from one phase to another phase, that means liquid phase to solid phase. That is why what happens, there is coming a what it is called step, that you can see. Why this step is coming? That thing generally due to what is called latent heat effect, generally these types of things is coming. Apart from this thing, due to phase change generally also this thing coming, this you should keep it in mind. Now, so along weld line generally these types of thermal profile is, you can say, is moving relative to the weld center line along the welding direction, how it is moving, that I am just showing. So, this is the relative temperature profile, how with relative position of weld center line, how the temperature distribution generally is there for a particular time t, if the welding speed is V, how it is there, that I am just going to show. Okay. Now, this is the temperature distribution along the weld line that I am showing. This, why I am showing this thing? So, you should have some idea how this temperature profile generally is varying. So, at weld center line there will be a molten pool. So, in this molten pool zone also, this molten pool temperature also at the boundary level, it is gradually decreased. At the center of this whirlpool you can see there is a high temperature, and in front of this molten pool zone there is generally solid material. Due to conduction there will be also some rising of temperature for that zone which is not affected by this welding heat source. There the temperature will be let us room temperature, what I am telling, understand. Similarly, at the back side also generally you see, you will observe if the well length is sufficiently very high, then also you will see this temperature distribution generally due to solidify and cooling down, this temperature profile gradually decreasing, and after that it will also goes to very lower temperature. And now we will discuss about whatever the governing equation I have shown. Based on this governing equation and what it is called some suitable boundary condition which I have already discussed, and initial condition. Generally, first of all, the solution we obtain for fixed heat source in welding. What are the solution we obtain, that related things I will now discuss. I will not drive these things here because for derivation purpose for one solution will take one lecture. So, there will be multiple number of solutions are there. So, I will just show how this solution is coming. This solution is coming generally how this solution is coming based on the governing equation which I have shown. So, what is fixed heat source in welding? Fixed heat source in welding means here generally the concept of this instantaneous and fixed heat source is widely used in the theory of heat conduction. Here I have written this fixed heat source, this concept generally we use. What is this? Little bit I am discussing this thing, then it will be very clear to you. Generally, in case of fixed heat source, let us consider this is a plate. This is a plate, let us. So, fixed heat source means this fixed heat source can be categorized into two types in this what is called analytical model based on this governing equation. One is called point heat source, another one is called what? Line heat source. Second one is called line heat source. So, what is point heat source? Point heat source means here generally we are putting the heat at a particular point, you can say. So, point generally consider it has what is called volumeless. Okay. Line heat source means here the heat is applied, in case of line heat source, heat is applied along a line, let us what happens, here we are applying the heat along the line. So, in case of line heat source, here we consider generally through the thickness our temperature gradient is 0. This you should keep in mind. That means, through the thickness we are considering there is a constant heat. So, due to this constant heat through the thickness we are considering there is no temperature gradient. Okay. So, there are two different types of heat source generally we will show in analytical solution. One is called fixed point heat source first, after that I will just discuss fixed line heat source. So, first of all, if you apply fixed line heat source in a particular plate at a time t equal to 0, and let us consider the initial temperature of this plate is, so T I am writing is T room temperature is let us T 0, initial temperature of this entire plate is T 0. Then if you instantaneously, if you apply a line heat source through the thickness of the plate, then what should be the temperature distribution at any point P, of this plate, that I am going to show. So, in a line heat source, instantaneously generally we apply a heat there, after that generally what happens at time t equal to 0 instantaneously we are applying the heat. After that what we are doing, we generally checking due to this heat what should be the temperature variation at any point of this plate, that we can see. So, that things that the solution of these things is coming how? Based on the governing equation which I have shown in first slide, and I have also written some appropriate boundary condition and initial condition. The solution directly I am showing in case of line heat source, what should be the temperature rise or temperature distribution. Let us at a point P, the temperature T, this temperature T at a point P can be written as T minus T 0 equal to your J by G K 4 pi T exponential to the power minus R square by 4 alpha T. This you should keep it in mind. So, this is the solution. Now, what happens from here, from this equation you can see this temperature at a particular point P. So, this temperature, let I am writing P. So, with time, this time also I have written time, this is T is time, here G is called thickness of the plate, I have already written G is called thickness of the plate, T is time, and this J is heat input in joule, this is called heat input in joule, I have already written. And here one thing you should keep it in mind, in line heat source what we generally observe, here top side temperature and bottom side temperature is same. So, here in case of line heat source, through the thickness your temperature gradient is 0, through the thickness let us consider here you can say del T by thickness direction let del Z, this del T by del Z is equal to 0, through the thickness no temperature variation, that means whatever the temperature will be T at top side, middle side also temperature will be this T, and bottom side also temperature will be, any point your temperature through the thickness will be same at a particular location, this you should keep it in mind. Then with time also how it is varying, this T, if we apply instantaneously some heat at T equal to 0, after that if you will check at any location of the plate how the temperature is coming, that you can easily calculate by using this following equation, this you should keep it in mind. This is the solution of fixed heat source. Till now we have not discussed moving heat source which is actually taken place in case of welding. You will observe that one heat source is moving along the weld line or one electric arc is moving along the weld line, that related things also I will discuss after this. Now, here in case of, as here z coordinate do not have any, you can say through the thickness as temperature gradient is 0, that is why you can say here R, whatever the R we are considering, this R is equal to, let us from this point distance this R. So, this R equal to what? Is x square plus y square, z square term is not coming. Now, this is the fixed heat source for line heat source case solution, and for fixed heat source in case of point heat source condition, this is also called 3-dimensional solution, because here in case of point heat source through the thickness of the plate your temperature gradient is not 0, through the thickness also your temperature will be varying. So, here directly I am showing how the temperature at a point P, let us T, here I am writing Tp minus initial temperature of this plate is T0, this will be equal to your what? J by rho C 4 pi A alpha, actually 4 pi alpha T into all to the power. So, J by rho C 4 pi alpha T whole to the power 3 by 2 exponential to the power minus R square by 4 alpha T. So, this is the solution for point heat source. Point heat source means in case of a plate which have a thickness, through the thickness is there. Now, instantaneously at any position if we apply a temperature or if we apply heat J, let us here I am applying a heat J in joule at time t equal to 0. Due to this thing at any point P, what should be the temperature T, that we can easily find out. So, from here where we are applying the heat, let this is O point and this is P point. So, here OP is equal to, you can say, your R. So, this R generally here I have already told R you can retain as is a function of x, y and z, x square plus y square plus z square. That means, through thickness also it is varying. This you should keep it in mind. This is called solution of point heat source in case of fixed heat source condition. Okay. Now, we will go to discuss in case of moving heat source how what it is called solution will be there in case of a first point heat source case. How the what is called temperature distribution is there. So, the concept of this moving heat source generally is very popular in case of welding technology for prediction of thermal history of a welded structure, that you can say, or you can say in a welded plate how the temperature is varying over a plate due to a moving heat source. Especially here we will discuss the moving point heat source and what is its solution for thin plate case and thick plate case, that related things also I will discuss in this lecture. So, the basic theory of this what is called generally heat flow generally applied to the moving heat source by a very popular scientist in the field of welding. His name is Rosenthal. I have written here, his name is Rosenthal in 1930, that is actually in late 1930 you can say. So, is a rather very popular analytical method for calculating of thermal history. Thermal history means over the entire plate structure due to welding how the temperature distribution is taken place, because thermal history prediction is the most important aspect required to do the further analysis of a welding structure, because due to this thermal effect only rest of the changes is coming. Rest of the changes is coming in the sense due to the thermal effect only there is coming what it is called microstructural changes, there is coming the residual stress, distortion and all the things. How? Because due to this thermal effect in welding, generally in case of welding there occurs some uneven expansion, contraction, and what happens due to this uneven expansion and contraction there occurs some what is called residual stress distribution. Due to as well as this residual stress distribution they are due to some cooling rate phenomena taken place also, there is occur some cooling phenomena also. Depend on cooling rate generally your weld zone microstructure, then what is called surrounding heat affected zone microstructure is changes. So, what happens, the most important aspects of you can say welding process analysis is what? Thermal history prediction. If your thermal history prediction will be accurate, then what happens, rest of the prediction, that rest of the prediction in the sense like prediction of residual stress distortion will be also accurate. That is why the basic concept or fundamental behind thermal history is very much essential to know. So, till now we have got the idea in case of point heat source how the temperature is coming. Now, in case of a fixed heat source how the temperature distribution is coming over a plate. Now, we will go to discuss in case of a moving heat source, especially if it is a point moving heat source how the temperature is coming over the entire plate, that related things now we will discuss. That I will discuss in case of a thin plate case as well as thick plate case. So, this moving heat source generally was invented by a very popular scientist, his name is Rosenthal. So, this is a analytical solution of this governing equation you can say for which is popularly used what it is called in case of welding thermal history prediction.